Okay, so we ended today's lesson with formal charge and the bell ring. And so for right now, I'm going to skip formal charge, and we're going to come back to it on Monday when I'm back in class. Because quite frankly, I feel like this is a discussion we need to have verbally so you can ask questions, because it might be a little confusing just the first time you see it. So we're going to just go straight into the molecular geometry, because you need that to be able to do your work today. And of course, molecular shape or molecular geometry is a repeat from last year, but we're going to go a little bit more in depth, okay? And so let's just start with this, molecular shape. Remember the Vesper theory, valence shell electron repair theory is the one that tells us our shapes, or predicts the shapes, because it is still just a theory. So the molecular shape obviously changes the more sigma bonds, which are single bonds, that we put on, plus the lone pairs, because if you recall, the lone pairs take up a certain amount of space around the atom. So here we have something that we have not talked about before. We have electronic geometry, which I see that that's got a big misspelling in geometry. Not my notes, not my misspelling, I can't claim it. Anyway, there's molecular geometry and there's electronic geometry. And quite frankly, I feel like when you understand the two, the molecular geometry makes more sense, because we just tell you in Chem 1, oh, trust, there's some lone pairs, they take up space. But this is going to show you how they're actually taking up space. So when you have the bonds and the lone pairs on the central atom, and you have 2, 3, 4, 5, 6, etc., these are the basic shapes they're going to take for their electronic geometry. Okay? When you're looking at molecular geometry, you basically ignore the lone pairs that are there. So here we go. So we have the molecular Vesper model and shape. So it's the arrangement of the atoms bonded to the central atom. So it's not necessarily as a structural pair. Lone pairs, we said, have different repulsions because of the electron-electron repulsion, so they take up actually a little bit of space. So they have different repulsions since they are experiencing a pull from only the nucleus as opposed to two nuclei. So like when something is bonded, those electrons are experiencing an attraction for both of the nucleus, but the lone pairs are only feeling it for themselves, for just that one particular atom. So each lone pair, of course, repels, and they try to avoid each other. So this works well for elements in the S and P blocks. Vesper does not necessarily apply to the transition elements. There's a few exceptions, quite frankly, because they're forming ionic bonds. So we're mostly talking about things that are going to be sharing, because that's a molecule. Remember, an ionic bond doesn't have molecules. We call those formula units. So let me take that off, and then we can go down to the next page. So molecular shapes for the central atoms with normal valence, so no more than 4 structural pairs, if the atom obeys the octet rule. Since no lone pairs are present, the molecular or structural pair of electronic geometry is going to be your tetrahedral shape, because you've got 4 things bonded on it. Okay, so the electronic geometry for the NH3 is actually tetrahedral, but its molecular geometry, of course, is trigonal pyramidal, because these are taking up those space around the atom, because those are the lone pairs. So we end up with a trigonal pyramidal molecular geometry, which is what we would have done in Chem 1, but it's electronic geometry. Basically, we can kind of think of these as areas of electron density. That kind of helps you with that, areas of electron density. And that means you've got bonds or lone pairs. And so you have areas of electron density around that atom. Okay, so this has 1, 2, 3, 4 areas, so that's going to make it a tetrahedral shape. But its molecular shape is trigonal planar, because this is just the shapes of the atoms down here. Okay? All right. Water has 2 lone pairs, so it still obeys that octet rule, got 8 around it. So again, because it has 4 areas of electron density, it's got the 2 bonds and the 2 sets of lone pairs. So its electronic structure would still be tetrahedral, because it's got 4 areas around it, because it's obeying the octet rule. But its molecular geometry is bent. Okay, And that kind of explains to you, in Chem 1, we just kind of like told you, here's the angles, you got to know them, okay? Well, this is showing you why those angles do what they do, because really, the original electronic geometry should be the 109.5. But of course, these bonding pairs right here and right here are taking up space, so they push those down. So you end up, instead of getting a 109.5, you get 104.5. Okay, so there we have those 3 examples of the methane, which would have the 109.5. Methane, because remember we're assuming these lone pairs are right here on ammonia, so that's why these are pushed down, and then you got 2 lone pairs on there, so they push them down even further. So to determine the geometry, you have to do the Lewis structure. You cannot skip that step. Okay, so it helps to then describe the electronic geometry, or it's what's bonded to it, or its areas of electron density. And then you focus on only the bonds to know it's molecular. So only the bonds is what the molecular is. So let's do a couple examples and see if you can wrap your mind around what we're doing. Okay? So here are some molecular shapes for central atoms with expanded. Okay? So only elements, remember above energy level 3, or 3 or higher, excuse me, can expand their octet. And so that's because they have those d orbitals, and so they can expand and have a 5th or 6th bonding site. The combination of the 1s and the 3p's provide the 4, and we're going to get to hybridization next week. We're not going to do it until I get back. But then when you have the 3rd energy level or above and you've got that d orbital, you can add a 5th or a 6th site. And so we're going to look at a couple of those. Okay, so here is some other things that have more. Remember, we're looking at the bonds themselves to determine the molecular geometry, but we're looking at areas of electron density to determine the electronic geometry. All right, so let's look at a couple of these. This one just says describe the molecular structure of the water molecule. So for the water molecule, you have 2 bonding and 2 non-bonding pairs of electrons. So we did that example earlier. So you're forming a V shape. I don't know why they're calling it V shape in there. We would call that bent or angular. Bent or angular. And we'll get to polarity of the molecules here in a minute. And then your bonding angle would be 104.5 because it's distorted from the original 109.5 of the tetrahedral electronic geometry. Okay. The next one says when phosphorus reacts with excess chlorine gas, the compounds of PCl5 is formed. So it wants us to predict the geometric structures of PCl5, PCl4, and PCl6-. So I'm going to have to give myself some more space because I for sure will not be able to write it in that tiny little space. So first one we have is PCl5. That one's pretty straightforward. So we're going to do our PCl5. We're going to have 7 times 5 electrons for chlorine, plus phosphorus has 5, so we're going to need 40 electrons. So then we're going to just simply draw our phosphorus and put all of those on there, and then give everybody their lone pairs, and we will have 40 when we do that. Okay, and it's because there are no lone pairs on this central atom, it's going to have the same molecular and electronic geometries. So molecular and electronic geometries are going to be trigonal by pyramidal. And I just, let me spell that correctly. Okay, so that's that one. The next structure they wanted us to do was PCl6. Cl4 plus, okay? So this time we would have 5 for chlorine. 4 times 7 is 28.
Vanessa?
Hold on one second, please.
Sure.
Okay, sorry about that interruption. Let's keep going. So we're going to draw the PCl4, and it's got a plus 1 charge, so we're going to have to add an extra electron. So when we do that, we should get 32 electrons. So we're going to draw our structure. So let's do it in a different color so that we're not getting confused with the two structures. So we're going to have P, and we're going to attach 4 chlorines. And then we are going to give them their lone pairs. And make sure everybody's got their 8. Hopefully you can see all those. They're very faint, but hopefully you can see them. So if I count those, we're going to say 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. And we're good to go. I realized that I gave this guy a little too many, so I'm going to take his away. That's why I didn't count them, because I just realized I was getting a little crazy with my dots. So I have 32 electrons, so my structure is good, except for I need to give my brackets, because it is an ion, and give it a plus sign. So its molecular and electronic geometry are going to be the same, again, because there's no lone pairs. So we've got 4, so we are at tetrahedral. We've got 4 things bonded to it and no lone pairs, so it's got 4 areas of electron density, so we have tetrahedral. Okay, and then we'll do the last one, which was the PCl6 with the -1 charge. So now we're going to need, we've got 5, and then 6 times 7 is 42. And then we have a negative charge, so we need to add another electron for that. So this one we took away. So we should get 48 electrons that we need. So we're going to draw the P and give it 6 chlorine. That goes with that one. So let's not give them too many dots this time. Everybody gets its 8. The dots are so tedious. Okay, now let's count them up and see if we get, oh, let's do our brackets. Forgot the brackets. Brackets with the -1. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 41, 42, 44. Did I miscount one? 46. I thought that did I miscount one? Because when I did it on my paper, I had enough. Let's count again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Okay, I just miscounted. All right, sorry about that. So this structure, because it has 6 things bonded to it, if you look back at that, and there's no lone pairs, so both its electronic and molecular geometry are going to be octahedral. Okay. As far as for bond angles, tetrahedral is going to be the 109.5. Trigonal bipyramidal, you're going to have 2 bond angles at 90 degrees, and then you have 3 at 120. And then octahedral, they're at 90 degrees each. Okay? So, if you're still writing that, pause it. I'm going to move on, and then you can start the video back. Okay, so that was that one. That took a lot of space. So let's keep moving along here, and let's look at the bond angles for structural pairs. If you are linear, of course, you're going to be at 180. Okay, so your linear things are going to be 2 things bonded to it, no lone pairs. Okay, so beryllium chloride would be an example. If you are trigonal planar, and trigonal planar is going to have no lone pairs on it, so it's just going to be spread out to an even 120 all the way around. If you are at 4 for tetrahedral, you're at 109.5, so all of those are, and this is molecular, well, it's electronic as well if you've got 4 areas of bonding density or electron density. So we call that tetrahedral. Do not call it square planar. That's a different structure, okay? For trigonal bipyramidal, which is 5 things bonded, no lone pairs, you're going to have 3 angles at 120, 2 at 90. Octahedral, of course, is 6 of them at 90. So when we throw some lone pairs on here, though, we screw everything up, basically, okay? So you have to change the molecular geometry when you're adding lone pairs on there. And water and ammonia, remember, were those examples. So that brings us to molecular polarity, okay? And if you remember, you can have bonds that are polar or nonpolar. Of course, you can have ionic, but they're not going to show up here. So you can have bonds that are polar or nonpolar. But that is not the same as your molecular polarity. In other words, what is the polarity of the entire molecule? Okay? And so that's where those dipoles are going to come in. All right? And so remember, a dipole moment is the separation of charge where you get the slightly positive and the slightly negative ends of a molecule. And it's based upon the way that they're sharing the electron. And so let's look at water right here, because water is polar. So if we look right here, we know that the oxygen gets the electron more because it's more electronegative. So we get these slightly positives and these slightly negatives right here that show that our molecule is not sharing equally. So we draw our vector arrow right here, and we always draw from the positive toward the negative. And so this molecule is got a slightly positive side and a slightly negative side. And so that's called a dipole moment. Okay? So what we have to look at when we're drawing these molecules is, are they like this, opposite, or sometimes they will actually cancel each other out, and then it ends up being a non-polar molecule. In Chem 1, we said symmetry. We said, oh, just look at the molecule and see if it's symmetrical. If it is not symmetrical, then we said it was polar. If it is symmetrical, we said it was nonpolar. Do not, I repeat, do not use those words on the AP exam, okay? That's an example of generalizations for Chem 1. Here we have to talk about the dipole moment, or the canceling out of the dipole moments, to determine whether it's polar or nonpolar. So do not tell me, oh, it's symmetrical, it is a it's a nonpolar molecule, because you will not get credit for that on the AP exam. So another example of generalities in Chem 1, but now we're going to be big chemists and we're going to use the real words, okay? So if we look at this one here, and I'm going to draw this out separately. So we're going to draw this NH3, okay? And we know by looking at this NH3 that they're not going to share equally. And we know that the hydrogens are going to are slightly positive. So what you can do is you can see that each, let me do it in a different color so it shows up better. Let's do it in, okay. So we can draw each vector arrow for each bond, and we see that it goes this way and then this way. So we can see that we've got overall this for our dipole moment. So you can kind of see how they'd be additive. So this would definitely be a polar molecule. So anything, I just realized I didn't give that enough lone pairs. Anything that has lone pairs on it is going to be a polar molecule, and that's like guaranteed. So this is going to be polar, and so is that water. And hopefully you at least remember that from Chem 1, that water is polar. Okay? So if the octet rule is obeyed, we're on this next bullet, which is it is in both water and ammonia, and all the surrounding bonds are the same, even if they're very polar, then the molecule would be nonpolar since it all has its dipole moments. So next example is CO2, or carbon dioxide. So they're kind of, I don't know if you can see that, but faintly showing that their dipole moments from carbon to oxygen cancel each other out. So I have slightly negative, which we show with that little small delta, and a slightly negative. So this would be a nonpolar because it in Chem 1, we would have said, oh, it's symmetrical all the way around, it's nonpolar, but we're showing that our dipole moments are canceling each other out, okay? And, of course, dipole moments are vector quantities, but in chemistry, you know, physics words are bad words to me. I don't like them. Don't tell Mr. McGowan. Okay, so let's look at a couple more and see if we can think. So we're going to do these 4 examples, and we're going to draw their structures because it's going to ask us in a little bit to rank them. So here we have methane, and if you don't have methane memorized by now, I highly suggest it, okay? So we have methane, and we're just going to draw structural formulas. We're not going to draw all the little gory lone pairs because that takes too long. So there's methane, so we got that one. And then we're going to do C, H, 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 and then a Cl. So we got that one. And quite frankly, it doesn't matter where you put that chlorine, just know that it can go anywhere because these are 3D molecules. Then we have CH2, and again, you could have drawn them next to each other or across from each other, it doesn't really matter. And then you have CH3Cl. And then lastly, we had CCl4, carbon tetrachloride. Okay? And again, we're not going to draw all the gory details there. Okay? So let's draw our dipole moments. Between the carbon and the hydrogen bond, obviously carbon gets the bond more, or the electron more. So we would draw all these like this. You'll see why I don't teach art. So our overall dipole moment would be plus right here to plus right here. So it's this, there's not a dipole moment. We actually wouldn't draw it that way. But you can see that we've got pluses all the way around. And so that, of course, is a non-polar molecule. Okay? When you're doing these, if it helps to look at it and you go, oh, it looks symmetrical, it's going to be nonpolar. That can help you think of it, but do not write it. Okay? Do not write it. Talk about the dipole moments. Okay? Of course, this one, we would have going this way, going this way, going this way. But when we got to this carbon-chlorine, it would be going this way. So overall, it would have a dipole moment that looked like this. So this would be a polar molecule. Okay? Same thing here. This side, we're just going to draw the slightly negative, slightly negative, slightly positive, slightly positive. So our overall dipole moments would be negative to positive. Okay, so definitely not canceling out, and so this would be polar as well. Same thing here, draw them, and you see the same thing, and then this one goes this way. So we would have negative down here, slightly positive up here. So this one would be polar. And then when we get to the last one, we've got chlorine all the way around, so our vector arrows are going to be going out, 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 and out. This was for that, okay? So this one would be nonpolar. Okay? If you're not finished writing that yet, pause the video and catch up. Okay, for each of the following molecules, show the direction of the bond polarities and indicate which ones have a dipole moment. Okay, well, we should be able to look at HCl and know right away HCl is hydrogen and chlorine, so the vector arrow is going to go this way because chlorine is definitely going to get the electron more. So this would be polar. And then we've got chlorine to chlorine, and it is definitely nonpolar because it's bonded to itself and it has no dipole moment because they're sharing equally. Okay? And then SO3, which it's telling us that SO3 is a planar molecule with oxygen spaced evenly around. So even if we didn't have to know or didn't know how to draw that structure, They're just telling us it's planar. Okay, so that means the oxygen are evenly spaced. So oxygen gets the electron more because it's more electronegative. So all of our vector arrows would look like this. They would all be going out, and so all the negatives are facing out. So this would be nonpolar. Okay, and then it says CH4, which we just did. We're not going to do it again. And then H2S. And so sulfur is going to have 2 lone pairs on that. So basically H2S is going to look just like water, except it's going to have a sulfur. So your dipole moment is going to definitely go this way, and so that's going to be a polar molecule. Okay? And again, they're calling it the V-shaped. I've always called it bent or angular, so I think you'd be okay with doing bent or angular as well. Okay, if you're understanding it at this point, you can stop the video and start on your homework. I'm going to do just a couple of more examples. I'm not going to do the 13 because we're getting tedious, but I do want to talk about double bonds. And just real quick, I'm not going to draw those either. But basically, double bonds, when you're talking about molecular geometry, it's still one area of electron density, and so it would follow these same rules. So we did CO2 earlier. When we did CO2, we drew it like this. And so there's multiple bonds there. And so it's still just, even though there's 4 bonds on carbon, it's still 2 areas right here of electron density, and so that would be linear, okay? And so that's the way that works. All right, I think that this is going to be about almost the end of the lesson so that you can do your homework. Sorry it's so long, but we've, like I said, we're up against a deadline. This is just recapping some of the characteristics of ionic bonds and covalent bonds, so I'm going to let you read through that very quickly because, quite frankly, you can read, and I don't need to read to you. One thing that I do want to make note of is that you realize that compounds that are ionic have that higher melting temperatures, and that they're crystals. They are stronger than covalent bonds, so make sure you know that. And then there's some characteristics of covalent bonds listed here, and then also some characteristics of metallic bonds. Because I don't think we actually talked about the characteristics when we were talking about the bonding, so there's a good recap. And then I'm going to leave you with this. For this unit, this part and the part we're going to do next week, here is the thing to keep in mind. Draw the Lewis structure. Don't get lazy. A lot of times, if you just try to answer it by memory or you think you know what the Lewis structure looks like, you get it wrong. So draw the Lewis structure, okay? And then also when you're talking about polarity, do not say the word symmetrical, okay? All right, I will see you guys on Monday. I hope you have, even though it's only Thursday today, when you're watching this, I hope you have a fabulous weekend.